I'd like to go back to this question from before the break. What happens if we change this thing to something other than 0? Right, so if we put, say, a 1 here. Right, so if we put a 1, what changes? Well, we started off here, now we have this is equal to 1. So now, when we rearrange, we get (1 minus 2x). We divide out. Okay. So what happens is we obtain a parallel line with a different y-intercept. Okay, so we get a different line like this. Okay, so this lower guy is where we dot to 0, and that's orthogonal. Now we dot to 1. So someone mentioned that the line moves up. That's perfectly correct. Okay, the line moves up. They stay parallel, though. Okay, so this is a nice way to define lines and planes in space. And you can actually do this in higher dimensions as well. Okay. So now we're going to, oh yes, question?
Are they still orthogonal even if the dot product isn't 0?
Aha, right. So now, yeah, so that's a good question. Hello. So yes, this set of vectors is still, as a set, it's orthogonal to 2, 3. Okay, so as a line in the plane, it's orthogonal to that vector. But the elements are no longer orthogonal. They form some different angle. So as a set, this line and this line are orthogonal. Yeah. So a subtle distinction, very good. Okay. So now we're going to take a brief excursion into higher dimensions. So what we're going to do is temporarily move to section 2.5. Some of the calculations that we get involved in 2.5 will lead us to backtrack and do 2.4. Okay, so we'll talk about 2.4 today once we need those tools. Hello, welcome. Hello. Last year I trained people to bring me coffee after the break. Excellent move. Anyway, let's see lines and planes in space. Okay, so this notion of orthogonality is very, very, very helpful. So a plane through the origin lots going on in that definition. So a plane to the origin is an equation of things that dot to 0 against something called the normal vector. Okay, so what's that simulating? This is simulating our case when this thing is 0. When we have a line that passes through the origin 0, 0, and is all of the stuff orthogonal to some given vector. So if we do this in space, now we've got a direction n, and we're looking at the plane of things orthogonal to that direction. So I'd like everyone to repeat after me to try this out. So take your highly scientific normal vector, yeah, hold it up, yeah. There's like one guy who's like, oh my God. But this really helps. You'll learn this way better if you actually do this with your hand. Now hold your other hand flat, okay, and repeat after me. The pen is normal to my hand. Okay? Now move them so it's still 90 degrees. Okay? The pen is normal to my hand. You guys are great. I love all of you. Okay, but this is a weird geometric relationship. So this is a way of defining planes. Okay, and it's this idea that normal things should be at a 90-degree angle to the object under consideration. So I want to show you what this looks like on a 3D graphing thing. So we're just going to use the computer to sketch. Okay, so we're going to sketch this guy on the computer. But to do that, we need to do a little bit of algebra first. Okay, so we get here. We're going to rearrange to solve for z. Something like this. Okay, so when we plug this into the computer, I really like this app, GeoGebra 3D Calculator. So we'll plug this in. And we get some kind of plane. So drawing these diagrams is really, really hard. People didn't figure out how to draw in perspective until like 1500. Okay, it took a while. So we're not going to ask you to draw many things in 3D, but you'll appreciate them better and understand them better if you graph them and look at them in 3D. Okay, so we call this a plane through the origin because it contains that point 0, 0, 0. So we go to the origin there, and you can see that in the x direction, y direction has got a bit of slope. So there's a plane through the origin. But we can also make this dot product equal to other things, and that'll have the effect of shifting things up or down. Yes?
Kind of unrelated topic, but doesn't that make it an eigenspace because it's a zero vector?
Sorry, come again?
Doesn't it make it an eigenspace because it's a zero vector?
It is the eigenspace for something.
Yeah.
There is a linear operator that has that as an eigenspace. But we'll talk about that next lecture. Okay, so this is through the origin. Now let's move it up or down. So now we'll say that the scalar equation of a plane is where we dot and we get some output c. Okay, so this has the advantage that we can move this plane away from the origin now. Move it up or down. Okay, and we can contain particular points. So so the scalar equation of something is called a scalar because it outputs a fixed number. Okay, so here we've got a point on our plane. We've got a normal. So the only thing that we're missing is the value of c. Okay, so we'll find the value of c here. So that constant is the same for all points on our plane. Okay, so our scalar equation for this also write this in the format So I'll graph that guy as well. Get some plane that does not pass through the origin, that's raised up a little bit. We plot that point. At that point 1, 1, 1, we see that's contained on our plane. Look at that little ping pong ball. Oh, sorry, 1, 2, 3. Oops, oh no. Oh no. Right, sorry, have I switched my normal? I have switched the normal. Oh no. Sorry, our normal should stay the same. We have this normal. So we get this plane, and we have this ping pong ball living on it.